In the last lesson, we learned about a neurological patient, HM, who had a profound memory disturbance after surgery. HM had the inferior part of the temporal cortex, along with the hippocampus that lies within the temporal cortex, removed on both sides to treat epilepsy. And as a consequence, he had anterograde amnesia. He could not make new episodic memories, and he had a gradient of recall, so retrograde amnesia in a gradient-like fashion, although seemed to have access to more distant episodic memories. So why did he have these symptoms? It led researchers to speculate about the function of the hippocampus in the memory system. And this idea came to be called system consolidation. Here's how it would work. Here's what neuropsychologists thought was going on. The hippocampus has an interesting set of connections to the rest of the brain. It receives information from the major perceptual regions of the brain. For example, the visual cortex in the back of the brain sends visual information to the hippocampus. The auditory cortex in the temporal lobe sends auditory information. Tactile information is sent from the parietal lobe. So it's as if the hippocampus is integrating all of the perceptual information that we might be getting during an episode, during a lived experience. So the idea is that during the encoding of an experience, and encoding we mean that the brain is sort of just processing the ongoing moment. During the encoding of an experience, the hippocampus integrates information from high-level perceptual areas, representing complex objects, along with a spatial frame that situates objects in a context, and that all constitutes an event. So the hippocampus is well positioned to integrate what's happening to us at any given moment. Perhaps this is the key first step in making an episodic memory. Then the idea is the hippocampus helps to transform a recent memory into long-term memory stored in the cortex. And presumably regions that were activated during encoding would be participating in the long-term storage of that memory. So notice then, during encoding, the hippocampus is integrating perceptual information to form an episodic memory, but then the hippocampus is instrumental in helping the brain, in a sense, transform the episodic memory into one that is stored in the cortex. And this would help to make sense of that gradient. Recall the gradient of recall. Because the hippocampus, after an episode, the hippocampus is still involved in transforming a memory. And if that transformation has had sufficient time to happen, then, we'll see in this next picture, then other regions of the brain can retrieve the episodic memory, and you don't need a hippocampus. This would explain why HM was able to retrieve information about distant events in his life, even though he did not have a hippocampus. So the episodes had been stored in the cortex and could be retrieved by other systems of the brain. So, remote memories of certain kinds can be retrieved without the hippocampus. Frontal cortex regions may be able to reactivate a memory without the hippocampus. So retrieval of remote memories and not recent memories suggests that the memory of an experience undergoes a transformation over time, becoming less hippocampal dependent as cortical regions store the memory. This idea that a memory is being transformed over time came to be called consolidation. So under the standard consolidation theory, the gradient of recall here reflects the time course of consolidation. More remote memories have had sufficient time for consolidation, so the cortical representation for remote memories is stronger than for recent memories. Fully consolidated memories are hippocampus independent. They can be retrieved without a hippocampus. A hippocampal lesion, like HM, interrupts consolidation of recent memories, so they cannot be retrieved. So again, the idea is HM cannot make new memories because you need a hippocampus to integrate all the perceptual experiences that are happening in your ongoing life. So no new memories, no new episodic memories without a hippocampus to integrate that information in the first place. There's a gradient of recall here because the hippocampus is involved in the consolidation process, the transformation of a memory to where it's becoming less and less hippocampal dependent and more cortically organized, stored in the cortex. And then access to more distant memories, perhaps because those distant memories have already been consolidated, so you don't need a hippocampus to retrieve them. Other frontal cortex memory retrieval systems can reactivate those distant memories. This is standard consolidation theory. We can think of system consolidation with sort of a box diagram like this. Let's define what we mean. System consolidation is the post-encoding reorganization of long-term memory over distributed brain circuits. And the two circuits that we're talking about here are the hippocampal system and the neocortical system, so the cortical system. Now the idea is when we have an episode, when we're experiencing something, that initial storage is taking place in both regions, right? The cortical system and the hippocampal system. After all, the perceptual areas are in the cortex. It's just they feed that information also into the hippocampus. So the suggestion then is that the hippocampal system is making an important change so as to sort of store an episodic memory of that event. However, over time, consolidation takes place, such that the hippocampal system is somehow involved in a transformation where the cortex now becomes more important for retrieving that episodic memory, and the hippocampus becomes less important for retrieval. So in this standard system consolidation view, the hippocampus is of critical structure in the beginning, and then memory transforms in such a way that the cortex stores the memory for long-term storage, and the hippocampus becomes less and less needed for retrieval. Perhaps in the early days, perhaps the idea of the rationale for this system was that the hippocampal system might show faster decay of memories made here. The cortex might have slower decay, so it makes sense to transform the memory from a fast decay system to a slower decaying system. But we'll look at why consolidation happens in a later lesson. For now, then, consolidation is this process of the transformation, reorganizing a memory over distributed brain systems. And notice the concept of consolidation is inferred. So we're not witnessing it directly, we're inferring its existence by the existence of time windows of susceptibility to amnesic agents like a brain lesion. So we can think of system consolidation as the process whereby dynamic interactions between the hippocampus and the cortex allow the hippocampus to signal the cortex to store a version of the memory in the long-term memory system. Metaphorically, the hippocampus teaches the cortex to make hippocampal independent memories. Synaptic change occurs in those cortical regions originally activated by the experience. So we'll take one more look at the standard consolidation theory. So here we have a look at the cortex of the brain, the outer surface, and then here is the hippocampus has been pulled out of the temporal lobe. So the idea is that the hippocampal cells bind the sensory aspects together, forming an index or pointer that links separate cortical representations of the event. So remember, all the perceptual information gets fed down into the hippocampus, and so the idea is that the episodic memory or the episode is going to make changes in the hippocampus that represents an episodic memory for that event. Of course, the cortex was also processing the event, but that memory is weak at this time. The hippocampus serves as an index or pointer. It can reenact or reinstate the cortical version of the memory. So during consolidation, somehow, and we'll get to how this is happening at a later lesson, the hippocampus is somehow going to be involved in strengthening the cortical representation of the memory. So that over time, then, the cortex has a strong representation of the memory, and the hippocampal changes are no longer needed to reactivate that memory. So the cortical links are not required for episodic memory once the memory has been consolidated. So in this view, then you could remove the hippocampus and still have access to this episodic memory because it has already been fully consolidated. And this idea accounts for how HM seemed to have access to memories that were distant in his history. So, for example, his childhood memories or when he was a young man. In this original standard consolidation theory, it was as if the identical memory was moving to a new location. So originally it was sort of like a hippocampal memory that gets moved to the cortex. In the next lesson, we'll see that there have been some modifications made to the standard consolidation theory as new evidence emerges.